the energy gain can cause it to expand. And the expansion due to heat or contraction due to cooling, this can cause very large forces. So if we heat something up, the molecules will tend to vibrate, and that vibration then causes to expand. And that expansion can cause very large forces, and we're going to look at different applications and uses of these forces, and where we also have to take account of these forces when we're designing structures. This could cause the substances then to crack. These large forces could cause cracks or even to make a sound. For example, if you put ice cubes into a glass of water, you will hear the crack of them. As the ice cubes then heat up, they try to expand and it causes them to crack. Different substances expand at different rates. The expansion of gases when we heat them is much, much greater than liquids. And the expansion of liquids is in turn greater than that of solids. But equally, within each of the states, different materials will expand at different rates. And we're going to investigate that further, in particular for solids. When we were learning about thermal expansion in solids, we investigated a range of experiments. The first experiment we did was the bar and the gap. We have a bar that fits exactly into a gap. If we take that bar and heat it strongly with a Bunsen burner, we will find that the bar expands along its length, so much so that it no longer fits into the gap. And it will only fit into the gap whenever it is cooled sufficiently and contracted to fit in. A similar experiment was the ball and the ring. In this case, we start with the ball will not fit into the ring. And if we take the ring away and we heat it sufficiently, the ring will expand and the ball then will go through it. Also, the bar and the pin. This can be demonstrated in different ways. But in terms of the bar and the pin, the way that we would have done it in class was we would have heated the bar very strongly. And the bar would have expanded. And as the bar expanded, we tightened this nut and tightened it up and tightened it up and tightened it up. So at the full length. We then remove the heat and the bar tries to contract. The nut is very strong and holds it strong at one end, and as it tries to contract, at a certain point, whenever it's contracted sufficiently, it will have exerted such a force on this cast iron pin that the cast iron pin will actually break, thus allowing the further contraction. So there's quite strong forces evident there when it's sufficient to break a metal pin. Using thermal expansion then. When designing structures, engineers must take account of thermal expansion because different solids will expand at different rates, and engineers must know these rates and make allowances for this expansion in their design. Using thermal expansion then for different applications. Telephone lines. This is making use more of thermal contraction, you might say. Telephone lines are strung in such a way that during cold weather, if the lines try to contract, they don't snap. So we design in a certain slack in the lines. So the lines are put up in that they're slightly longer than the distance between the adjacent poles, so that whenever the cold weather comes and they contract, they still have enough length to contract without actually snapping due to the forces. Concrete slabs. Concrete slabs, whenever they are heated, even during the temperatures that we experience during our summers, which aren't considerably high, they tend to expand. And if you have the concrete built up very tight against each other, that could cause cracking and fracture of the concrete. So what they do is they design in an expansion joint, and this is basically an air gap between adjacent slabs which allows them to expand and contract without crumbling and breaking. Similarly, another application where expansion rollers are designed in is, for example, in a bridge. If we have a section of bridge, and bearing in mind they're often steel structures to hold them as well, if during hot weather the length of the bridge expands, we need to have a gap at the end to allow for that expansion. And in order to facilitate that expansion, where we have little support across a gap, we use rollers. So when it expands in one direction, it can roll out slightly, and when it contracts, it can roll back in the other direction. It's perhaps not that easy to see there. Other applications using thermal expansion. Railway lines. The metal railway lines will expand and contract due to warm weather or cold weather, and small gaps are allowed between adjacent rails to allow for that expansion. Although thermal expansion often gives us problems, it can also be useful. For example, fitting railway truck wheels. This is another diagram of a bearing and a gear. If we have where we want a shaft to fit in very tightly into a wheel, if we have the shaft made that it's slightly too big to fit the current gap, we can then heat the wheel or the gear sufficiently to allow the shaft to slide into it, and then whenever the wheel cools and contracts, it's held very tightly. So that's one of the ways that we can actually use thermal expansion. Another use of thermal expansion is a bimetallic strip. Now, a bimetallic strip is made of two strips of metal, different metals, which are joined together all along their length. The metals expand and contract at different rates when they are heated and cooled. So, for example, it could be iron and brass will expand more than iron when it's heated. We make use of that in different applications. When one metal expands more than the other, it causes the strip to bend, and it bends in the direction of the strip that expands more. If we look at this example, we have iron and brass, and they're the most common materials that are used simply because they have a different enough expansion rate for each of the materials, and also they're cheap and readily available. So if we have iron and brass and it's welded together all along its length, when we heat it, the brass expands more than the iron and it causes it to bend. So the brass side gets longer and it causes it to bend up around due to the forces of the expansion. These are frequently used as heat detectors and switches, and we're now going to look at two of the uses of bimetallic strips. The first one is in a fire alarm. As the temperature increases due to the fire, the brass will start to expand, and it will expand more than the iron. The iron also expands, but not at the same rate, and as the brass expands more, the strip will bend down, and as it bends down, it comes in contact with the contact, which makes the circuit which causes the bell to ring. So it completes the electrical circuit and rings the bell. So that's a fire alarm, and those would be similar to the fire alarms we have in school. A thermostat then. We have a circuit. In this case, the bimetallic strip is connected in the other direction. Whilst it's cool, the current comes in and flows around and heats and connects up the circuit, and it heats the heater, which is giving heat out to the room. As the room gets warmer, the brass then expands more and it bends upwards away, thus breaking the contact and turning off the heater. So this is the clicks that you would hear in some thermostatically controlled heaters, is the turning of it on and off. So the brass expands more and it bends away from the contact and turns off the heater. Then as the room cools, the brass starts to contract again and it comes back down to flat where it makes contact.